Okay, the next batch of problems is one of the more notoriously difficult things in trigonometry for students to understand. It's called identities. And I'll give you the short lecture on it now. You can compare these to equations. And these are the things you study in college algebra. They are solved. Okay, equations are solved. And for example, it's something like 2x plus 1 equals 3. Find x. That's an equation. And what you do is you subtract 1, you divide by 2, and you'll conclude that x equals 1. Identities, well, first, one more thing about equations. Not true for all values of x. That's the big important thing. An equation isn't always true. So if I plugged in x equals 3, for example, then I can do that. There's no problem in doing that. But I end up with a statement like this. And that's false, right? Because that left-hand side of this equality is equal to 7, and the right-hand side is 1, and that's false. So your job with an equation is to find the values of x that make the equation true. Now, on the other hand, identities, these are always true for all values of x. So, it's kind of meaningless to solve them. Because if you try to, then you'll end up with some statement like 1 equals 1 or something. It's nothing. What we do instead, we establish them. Or you could also say, or we prove them. And that's how this goes. So you'll be given some kind of equation, and it'll say prove this identity. Now both of them have equal signs. Okay, so let me make that clear. Both have an equal sign. Okay, which means both of them are mathematically a sentence. The only difference is, what do you do when you're presented with one? Often identities are things that, are sort of so-called clearly true. So, for example, 2x plus x equals 3x. That's an identity, okay? It's true for any x that you pick. If I plug in x equals 10, if I plug in x equals 12, 15, 60 trillion, it's still true, okay? So problems like this will look like the following. So in the homework, I assigned numbers 29 and 30. So let's look at 30. I said 29, 30, 31, 32. Did I assign 33? Looks like I did. So maybe I'll strike one of those from the list. So maybe let me do number 30, and I'll remove that from the homework. So here's section 9.1, number 30. Now, how does this go? So it says prove the identity, and they give you this equation: cosine x times tangent x minus secant of minus x, and then there's your equal sign, and then you get sine x minus 1. Now what they're claiming here is that the left-hand side and the right-hand side are identical. In other words, no matter what x I plug in, I get the same exact number out from both sides. So there's no use in trying to solve this. We don't really know methods to, if this was an equation, we try to find the solutions. We don't really know a method for that. But what we can do is attempt to verify the identity, to prove the identity. So this really is a proof, and my advice for this is to always start with the more complicated looking side, and that's often a subjective thing. What side's more complicated, and people may disagree, but I think it's pretty clear that this side is more complicated here. Okay. Now we'll have many more examples of identities in the next few sections, so I'm not going to do a lot of examples today, but there are, this will be sort of a persistent feature of the next few sections. So in this case, how do we do this? Now, what you do not want to do is write both sides down and try to do stuff to both sides. That goes back to, doing stuff to both sides is an equations thing. It's not an identity thing. In other words, we want to start here. So we start with cosine x times tangent x minus secant of minus x, and then we proceed from this thing using the properties of the trig functions. So my advice from earlier in the section still holds. Rewrite everything in terms of sines and cosines, and use whatever properties that you know. So for example, in this case, I have a tangent and a secant. I'm going to rewrite those things. Okay, so I have this cosine x out here. I have sine, if the tangent is sine x over cosine x, and the secant is 1 over cosine of minus x. Now, we know that the cosine function is an even function. So what's that mean? That means that the cosine of minus x, let me write it here again, cosine of minus x is cosine x. That's the even property of cosine. So I'm going to get rid of that minus sign in that denominator because I can't. They're equal. In fact, this expression itself is an identity. Okay, it's true for all x. So my first step here, I guess I'll use the evenness of the cosine function to say that this is sine x over cosine x minus 1 over cosine x. Now I'm presented with something multiplied times the sum. From algebra, the distributive property says that if I have something times a sum of things, then we think about the a sort of distributing in, right? It's ab plus ac. So the point is that it doesn't matter what a, b, and c are. They're objects, and we have this object times the sum of these objects. Now that minus sign makes it really a difference, but subtraction is really just adding a negative. So I'm going to distribute that cosine into both terms, and so I get sine x over cosine x times the cosine x, and the minus sign, okay, fine, and then I get 1 over cosine x times cosine x. Lo and behold here, the cosine x's cancel, they annihilate, and when you cancel, it doesn't become 0. That's something sometimes students make a mistake with. It does not become 0, it becomes 1. It's kind of like how 2 over 2, the 2's cancel and you get 1 out of it. So this term becomes 1, and this term becomes sine x. And look what we get. We get the final, this is the right-hand side. Whereas this was the left-hand side. So we have completed the proof of that identity. We've established that identity. So that's what proving an identity is all about. It's starting with the more complicated side, carrying out operations based on the properties of those trig functions step by step to start at one side and arrive at the other side. And that's all this is. So these are notoriously difficult because it's a change in the way you're sort of proceeding with problems. but it is not an impossible thing to to deal with. So let me do one more of these in this video. Where's my paper? I will have a better system going forward, I'm sure of this. But let's do another one. Example, prove the identity tangent theta times cosine theta equals sine theta. So again, I'm telling you it's an identity. You're not checking that it is one or anything like that. I'm just telling you here's an identity, and it's your job to write the proof to establish it. And there it is. So what I'm saying is that both these sides are identical for all values of theta. So again, my thought process here is that I picked the more difficult side to start with, and that in this case is the left side. So I'll start with the left and try to arrive at the right. So tangent theta times cosine theta. My general advice of rewriting everything in terms of sines and cosines is good here. I'll rewrite the tangent as sine over cosine, and the cosine that's on the right will just sort of carry along. And pretty much one step this was over. Those cancel, and I'm left with sine theta. So again, I've done the work in the middle to start here and end here, and that's it. So those are basic identity proofs. There will be more complicated ones moving forward.